Haiti, 12 days after the earthquake. Roger Billum is heading out of Port-au-Prince, looking for locations where the fault may have broken through to the surface. He needs to measure the amount of offset, how much movement there's been of either side along the fault. It's an essential first stage in working out the risk to Haiti of another deadly earthquake.
I have, in fact, got the coordinates of where the fault may have broken this road from colleagues who've been scanning the post-earthquake imagery. And from space, you can see lines of cracks that are lined up along with the fault through the mountain.
Even in the middle of a humanitarian crisis, it is vital to collect this kind of raw data as soon as possible after the tremor.
If you imagine the fault ripping, as it rips through the ground surface, it's going to offset roads, fence lines, houses, buildings, and other things that we can actually measure. And so this is a very important type of data that we need to collect quickly, because if we wait too long, people are going to tear down those houses and fix the roads and sort of cover over this natural rip that occurred through the earth.
The closest parallel to the strike-slip fault which caused the Haiti earthquake is the San Andreas Fault in California. It runs for over 800 miles like a massive scar on the landscape. As in Haiti, the San Andreas fault line marks the boundary between two of the Earth's tectonic plates. In 1906, an earthquake flattened the city of San Francisco, which sits right on top of the San Andreas Fault. 3,000 people died from falling masonry and the subsequent fires which swept through the city. Dr. Sean Gulick is a seismologist, an expert in movement along plate boundaries.
It's actually quite similar in some ways to the Haiti earthquake in that it happened in a place where two plates were sliding past each other along a fault plane that's roughly vertical. And the effect of that, while the earthquake magnitude was not extremely large, generated a lot of motion at the surface, which brought a lot of the buildings down, which at the time in San Francisco were built largely of masonry and caused a lot of damage.
Before the 1906 earthquake, geologists didn't really understand what was happening along the San Andreas Fault. They thought it was just random shaking. Then they noticed that fences had been offset, and that roads and railway lines showed the same lateral displacement. This meant that the land either side of the San Andreas Fault had moved horizontally, in opposite directions, along the line of the fault. And by measuring the amount of lateral offset, they could work out how much the fault had shifted. In the countryside outside Port-au-Prince, Roger Billum is looking for the same kind of evidence.
I'm expecting to see a series of cracks across the road. We actually may be able to measure the amount of lateral offset caused by the movement of the Caribbean plate. Oh, wow. Wait a minute. This is it. This is it. Yeah.
These cracks are bigger than anything he's seen so far. But do they show the signs of lateral movement he's been looking for?
One has to read the story. It's rather difficult to tell. The road has obviously been crumpled up. It's been squeezed. There's a slight evidence of offset, but not very much. This is probably not the main fault, just a secondary one. If you look over on the other side of the road here, you'll see gigantic cracks going deep down into the fill. You can look down here to almost 3 meters before you can see the bottom. Here it goes down about 4 meters, certainly into the soils on which this filled road has been made. And as you walk along here, you can see the road has actually been compressed here, bulged upwards. There's just 5 centimeters of offset here. I don't believe this is the fault.
But then he sent the coordinates of another possible site of the main fault.
1.7 kilometers. We need a road going off to the left, somewhere here. All right, let's go down it. Great. So, 600 meters. According to this We are now north of the cracks. So we might go along one of these side roads to have a look. Sure. 180 meters dead ahead. Somewhere here. 60 meters. What is this coming up? It looks kind of disappointing. We have no fault. We have a cow and a river. So I know where I am on my GPS receiver. I've got maps taken from space of this very spot, and I can't see the fault. And we'd looked very carefully. It means the fault must be a wide zone of deformation. It's not localized.
This could be a worrying sign. If he can't find the main fault line, he may be unable to work out the risk of another earthquake. In order to send a meaningful analysis of the earthquake back to his colleagues, Billum needs to get an overview of the fault. He has permission to ride in a helicopter, which will be flying right along the fault zone. From the air, he hopes to get a better picture of what's going on.
What we're looking for is evidence of surface rupture. We actually want to see the fault where it's broken the surface. We're just about to approach this valley where this very large earthquake occurred. The epicenter is over there, about 8 kilometers down. So as we're flying along here, I'm hoping to see any sign of faulting.
His trained eye finally spots something significant.
Ah, there's a fault. There it is on the hillside. Got a terrific view of about 10 kilometers of straight line, just like the San Andreas fault zone. This is a fault just like the San Andreas.
Since Billum's flight, geologists have learned that the main fault didn't in fact reach the surface. What he saw was a crack caused by the Earth bulging over the fault. Because of this, scientists are worried that the chances of another major earthquake have increased. The 12th of January quake caused an almost unimaginable amount of damage. But in geological terms, the earthquake itself, a magnitude of 7, was not especially large. How does Haiti compare with other earthquakes around the world? The plate boundaries where continents smash into ocean plates are often the most dangerous. One of the largest and most active runs south of the coast of Alaska. In March 1964, this boundary ruptured, triggering North America's biggest ever earthquake. The earth shook for a terrifying 4 minutes, and in places the ground was lifted by more than 30 feet. The quake caused a huge amount of damage to the city of Anchorage and the surrounding area. But just how big was this tremor? Seismologists developed methods to calculate the strength of an earthquake in the early 20th century. The best-known measure of magnitude is the Richter scale, named after the American seismologist Charles Richter. He studied the San Andreas fault in the 1930s.
The thing about magnitude scales, the Richter in particular, is that they are logarithmic in terms of the size of the earthquake. So an earthquake of magnitude 5 is 10 times more powerful than magnitude 4, and a 6 is 10 times more powerful than 5, and therefore 100 times more powerful than 4. So there's a huge difference between a magnitude 9 earthquake, for example, and a magnitude 6, 1,000 times.
The Alaska earthquake was a magnitude 9.2, the second biggest quake ever recorded. It was 160 times bigger than the Haiti earthquake. The greatest quake ever recorded hit the coast of Chile in May 1960. Its magnitude was a staggering 9.5, more than 300 times stronger than Haiti. But if Haiti was relatively small by comparison, why is there so much damage? Once again, geologists have looked to the record of earthquakes on the San Andreas fault for the answer.
A good example was the 1989 Loma Prieta earthquake, which was a strike-slip event, but it was not to the same magnitude or not the same length of fault ruptured as did in the 1906 event, but it was still large enough to cause significant destruction.
In 1989, San Francisco was rocked by the Loma Prieta earthquake, a magnitude 7. This was the same strength as Haiti. But in this earthquake, the damage across the city was extremely localized, depending on the type of rock the earthquake passed through. Many parts of the city were untouched. In other areas, houses built on unstable soil sank into the ground. In Haiti, Roger Billum sees a similar pattern of localized damage as he flies over the fault zone.
There are houses down there that are not damaged, which is kind of interesting because it's right on the fault.
But as he flies away from the fault, the amount of damage increases.
We've come out of the rock on a river lane. There's signs of considerable damage here. Total collapsed structure beneath us. I can't believe there was a house there, just a heap of rubble. I can see 5, 7, 8, 9, 10 completely collapsed houses.
It's clear that houses built on hard rock near the fault survived, while the worst damage is to houses built here on the soft sediment of the river basin. It's a process called amplification. As seismic waves pass through loose sediment, they become larger and more intense, greatly increasing the shaking on the surface. Back in Port-au-Prince, Billum realizes the underlying geology of the city may have contributed to the scale of the disaster.
The city is built on fairly loose sediments, so it actually amplifies the seismic waves. The epicenter is not very far from here, and the waves must have rattled past here, accelerating the building sideways and up and down. Apparently, people couldn't stand during the earthquake. The shaking was so intense. So the buildings were given a really thorough shaking.
But the geology of Port-au-Prince is not the only reason so many people lost their lives. The buildings were death traps.